Modulation, very important. That's AM modulation. Very important you know that one. That's an odd one to do. All right. Now, any other questions? A lot of time on that one. I should have already through it. One other thing about that one, that's a weird one. I'm just telling you, that's a weird one. Did you have a question?
Yeah, can we give a solution for number 4, the circuit problem?
Yes, absolutely. Why don't we do it? Give me
You have a source with a voltage of 20 e to the negative 3t ut.
U of T?
Yes. A resistor with 10 ohms and an inductor with 50 millihenries. And we're supposed to find voltage across the inductor.
I want to tell you two things about this problem. The first is there are no initial conditions. I put the current, or I put all the initial conditions at 0, I believe, on that one, right? So you don't have to worry about initial stored energy, which is important. Now the second thing is, later on I'm going to show you a trick to do all these in a domain called the S domain. Just like when you had circuits, you did all your problems that were steady state in the J omega domain, really? At a certain omega. Same thing here. But right now I'm going to do this thing the way it's normally done. When I think about this problem, and I look, I have a current I of T here, correct? And I have a relationship between current and voltage on an inductor. I know that L times the I dt is actually the voltage on an inductor as a function of time. Isn't that right, class? L di dt? If the inductance value is not changing with time. I'm going to tell you one other thing as a side note. Don't write it down, just listen. You're going to find the real value of voltage on an inductor is given by this. Voltage on an inductor as a function of time is the derivative with respect to time of the quantity L of T, that is the value of inductance that may change with time, times I of T. Now when you take a derivative of that, you get dL of T dt times I of T plus L of T times di dt. We always assume, at least in basic circuits classes and linear systems, that L's value does not change with time. There's the reason I put this on here specifically. Some of you are going to work for the government or work for programs like really, you're going to work for Boeing or Lockheed Martin and stuff like this, right? Well, they have devices that they create to get incredible amounts of voltage. It's really for electromagnetic pulse simulation or EMP flares to blind things. But here's how they do it. They take a core inductor. They take an inductor wound on a very powerful, really high explosive. And they drive a lot of current through that. And they take that, remember that it has an input and an output where they're getting a huge amount of current. And now they simultaneously separate the actual source of that current and short this thing across an antenna. It's a special type of antenna. And in doing so, they also explode the high explosive. Now what that does is cause the coils of wire to expand and change the inductance, as well as now all the current that was going there is shorted, and now the change in the value of the current is immense as well. This term right here is the term that causes this immense voltage that is possible. And it causes this immense amount of voltage that goes and causes a huge electromagnetic pulse event on a special type of antenna that I don't have time to get into. But I wanted to put this as a side note. It's not always L di dt like I've shown you there. L can be a function of time. And the voltage you get when it is a function of time, if it's wrapped around high explosive, the wire around high explosive is immense. And I mean billions of volts. So, anyway, this is the way it's usually done. Do you agree, class? Now, isn't this really our output? Correct, class? That is our output. So I can say di dt, is given by that. And I can further say that if that's the case, since that's VL of t, then if I write this equation, since I is a constant, I have 20 e to the minus 2t u of t here is equal to r, right? I'll just leave it as r for now. R times I of t, right? I of t. What? Oh, 3t, I'm sorry. 3, you're right. R times I of t plus L times di dt, right? This is one way to do this problem. Do you agree with me? Now, I could say, since I really want L di dt, I could write this as V of L, and I could say I of t here. I'll just do it right here. If that's the case, and take a look at this, I could go ahead and divide V of L, VL of t by L, and integrate it with respect to t, and therefore I would get I of t here would be equal to 1 over L, the integral from 0 to t prime here, or to t of VL of t prime dt. And that would be I of t. Do you agree with me? You can do that. Do you see what I've done there? If VL is L di dt, therefore I here would be 1 over L, the integral of VL of t dt from 0 to t. Agreed? And I can put that in. Matter of fact, why don't I do that? And that makes it easier, because now I can say this is R here times R divided by L times the integral from 0 to t of VL of t dt plus, and then this is just going to be VL of t, and that's equal to 20 times e to the minus 3t u of t. Now I'm just showing you different ways to write this. This one would be acceptable, but our solution would be an I of t. We would solve this with a Laplace transform of this, then solve, once we had I of s, we'd solve for I of t. And once we had I of t, we'd still have to take a derivative with respect to t times L to get the actual output voltage. Follow me on that thought, class? I'm going it where I'm getting directly VL. Now, when you do a Laplace transform of both sides of this equation, what do I get? What's the Laplace transform of this? You could tell me. Isn't that 20 just 1 over s plus 3? Work with me. Do y'all agree with that? So I'm taking a Laplace transform now of all this. So here, I get 20 over s plus 3. Are you with me? What's the Laplace transform of the next one? We have r over L automatically, don't we, class? You can't get around that. What's the Laplace transform of the integral of VL of t dt? Well, assume you know the Laplace transform of VL of t is VL of s. What happens when you have an integration? You know this one. Differentiation is s times V of, would be VL of s minus V of 0 minus, right? And integration of V would be 1 over s. Look at the properties, please. Look at the properties, class. So this is going to be VL of s over s. Please take a look at those properties in your book. How many see this property? 1? Make sure you see it. You remember, right? If you had x of t go to x of s, right? If I have dx of t dt, that goes to s x of s minus x of 0 minus, right? And if I have the integral of x of t prime dt prime from 0 to t, that goes as x of s over s. Make sure you can see that property. How many see that property? These three are real important. You got to know how to use them too. You all see it? Which property is it, please? 8. Property 8? Okay. Now what about this one? The second part is just VL of t, take a Laplace transform, it goes to? VL of s. Yeah, it's that easy. VL of s. That's it. All right? Now, work with me on this. What do I do next? I want VL of s, right? I'm leaving it as R over L. What could I do? Can't I factor out VL of s there? How about if I just, I'll just call it V of s for now. I can say I get V of s, right? And then I have the quantity 1, that would be the coefficient here. The coefficient here would be plus R over L, right? divided by S, and that's equal 20 over S plus 3. Do you agree with me? All right, how many see this, right? It's straightforward what I've done. Relocated things just to organize them so I can manipulate them. Now, the trick is that 1 over S term I hate. That's not going to help me. So I'm going to multiply both sides by S. Follow me? Everybody understand that? Both sides by S, so I get an S here. I get rid of this S, and an S over here pops up. Agreed? Can you see that in the back? You got good eyes, dude. What's my next step, anyone? You're right on topic here, if you're there. Break it, VS alone, you're right. And I get VS is what? Simply 20, right? S over S plus 3 times S plus R over L. Just leave it as R over L. Don't worry about the value right now. We'll get that later. You agree, class? How many see this? Can you see back there? You're struggling, it looks like. Everybody see that? All right. What does that look like? Sure looks like a partial fraction expansion. How many see that? And these are simple poles. Now, if this was S plus 3 squared, that would be a double pole. And if you have S squared plus 3S plus 5, that's a complex pole, usually. But this is a simple pole. These are the simplest ones. How many remember doing this back in the day when you had Laplace transforms? You don't remember partial fraction expansion? You kind of lived in that domain, didn't you? When you did that, you went ahead and say it's A over, these are simple poles, right? Just over S plus 3 plus B over S plus, what's R over L? So I'll give it a number. Anybody? R is 10, L is 50 millihenries, so it's 10 over 5 times 10 to the minus 2. What is it? What? Is it 200? Confirm or deny? 200? Is it 200? Yeah. Look, I'm just trying to get through this. You all agree? Now, anyone, how do you get A? What's up? Did you ever see the kids in high school on a test? Find A on his exam. He circled A. There it is. Smart. You won't get it from me now. It's failed. Anyway, what is A there? The value, numerical value. Or how do I get it? I call it the cover-up. You cover up the hole that it's over, right? And then you evaluate everything over there at S equals minus 3, right? Isn't the pole at minus 3? Correct, class? So this is 200, by the way, isn't it? 200. So if you want A, it would be equal to what? 20S over S plus 200 when S goes to minus 3. Now that's because the pole here is at minus 3. I'm putting this one down so you have it. Do you all agree? Right? I just what? Covered up the S plus 3. And wherever there was, whatever's left, I evaluated at the pole, which is S equals minus 3. Do you all see that in the back? What's the value going to be? Well, that's 20 times minus 3 or minus 60, right? Over 200 minus 3 or 197. That's an odd number. You all agree with that? Want to give me a value for that? I wish it was nicer numbers. You asked about this, so I'm glad you did. I want to go through this entirely, but I think you've got it by now. Give me a value. Pete, do you have that now? You did current? Is that how?
I just left it as fractions.
Yeah, all right. Just give me a value.
It's negative 0.3.
Minus 3.1?
Negative 0.305.
0.305, I'm sorry. Minus 0.305. All right, how do I get B? Same deal. Cover the S plus 200 and evaluate everything at S equals minus 200. Can you give me B? So B would be S goes to minus 200, right? And it would be equal to 20 minus 200 over minus 200 plus 3 or minus 197. And what is that number? 20 point what?
20.3046.
20.3406?
3046.
3.3046. Do y'all agree with that? We're not quite done. I'd like to do it right under here. If that is Vs, what is V of t? And tell me why. I'll just write it right here. VL of t.
Negative 0.3046 e to negative 3t u of t plus 20.3046 e to the negative 200t.
Two exponentials, right? He's right. He's actually right. I'll try to get this right since minus 0.305 for now. E to the minus 3t, right? And that's plus 20, what is it? 0.3046, right?
Yes, sir.
E to the minus 200t, and everything's times u of t, correct? Do you agree with that, class? Okay, now, isn't this value, this minus this 20, exactly at t equals 0? Please check this. Now, I got a point to make here. I want you to pay attention. Now listen, this is exactly 20 when t is 0. Follow me? You'll notice when t is 0, we got 20 volts here, right? Now, here's the deal. The initial conditions where everything was off, right? All of a sudden, a switch is closed, this is energized. But the voltage on the current in the inductor can't change instantaneously. Whatever it is on an inductor just before 0 minus, that's what it is just after 0 minus. It is 0 at 0, right? At t equals 0. Therefore, no current can flow the instant the switch is thrown, and therefore the voltage here is the source voltage, which is 20, and that confirms it right there. That's an important thing to know about inductors. Current can't change instantaneously. If there's none to start with, after everything's de-energized, there's none the instant after it's energized. Right? It slowly grows. I didn't get where I wanted to go, but it's important I do these problems. I'm going to give you a few more circuits problems like that. All right? Now, I'm going to get tons of email. Is there a quiz on Friday? There's a football game somewhere in there this weekend. I hate to give you a quiz on Monday for football weekend. How about we do this? It's a quiz on Laplace transforms related to this stuff we just talked about today. What can be fair? Don't look at me. All right? So be here, in other words. I don't care about Thursday night friends. You don't show up here? Yeah.